So thank you, Olivier, and thank you. I have firstly to thank also the organization to give me, it's a little bit high, it's for very tall people. And thank you for give me the opportunity to present to your community or some of our research. It's not my usual community. It's a little bit, it's always dangerous. I'm more a specialist of mechanics of material than architecture and structure. And, but it's a big honor. Thank you very much. And I wanted to share this honor with my colleagues, with Olivier. And it's the reason why I asked also Romain Ménil to come with me to present this, to make this presentation. So very quickly, I just present our laboratory, the Navier Laboratory. It's a joint center. It's a joint center between École des Ponts Paris Tech and two French research institutes, CNRS and IFSTAR. We are located on the Université Paris East campus. Yes, thank you very much. It will be difficult for you to. So we are just on the other side of Paris, near Marne-la-Vallée. And our researchers are devoted to mechanics and physics of materials, structure and geomaterials, from a testing, modeling, simulation point of view. It's quite a big laboratory. We are quite 60 researchers and 80 PhDs. 5 different research teams, 2 on reophysics and physics of porous media. It's really mechanics of material. Multi-scale modeling, geotechnics, and my team called Architected Materials and Structures. We are a little bit more structure, but our researchers are devoted to complex materials as masonry, for instance, discrete materials, or composite materials also. I'm a specialist of composite materials. And we made also research about structural innovations, and from a theoretical point of view, but also we made a lot of experiments from the scale of a material to the scale of a structure. And for free, and we have a specific test for scale 1 experiments. And it's the reason why 3 years ago we decided to develop a robotic platform for construction, because of course, and you here all know that, it's the future of construction. So Romain is a young fellow of my team, PhD, a young PhD about complex geometries, and he is now also in charge of this technological platform that he will present now.
Okay, thank you. So just a few words about the experimental platform that has been just launched this year. So of course the idea behind this platform is dates back from approximately 4 years ago, with the beginning of some PhDs in our institutions on discrete geometry, structural optimization, or digital fabrication. The physical platform is made of 2 robotic cells, one with collaborating robots that is devoted to complex milling or complex assemblies, and so that's what you see here. And the other platform is devoted to 3D printing of concrete, clay, geopolymers, or other materials. So this platform is, of course, it's a research equipment, but it's also thought to be a tool that will promote the learn by doing philosophy that we've been experimenting at the lab for many years now. You see here first realization that was done last year with our first robots, with the help of the first robots we got. So it's a wooden grid shell that was assembled in 1 week with 30 students. And just also a few words about the Design by Data Master, which is an advanced master in computational design. It's a partner of DMS 2017. And Francesco Cingolani is leading this master, and some members of the team are teaching. And just to show you, so that's the physical platform is a robotic platform, but we also gather several researchers from several disciplines, because we know that it's not enough to be expert in just one field of research if you want to be meaningful in terms of innovations in digital fabrication for architecture. So we have two labs, the Navier lab that Jean-François has just presented, and the Gaspard Monge lab, which is a computer science lab specialized in discrete geometry and deep learning. And we are also using now robotics, and we have industrial partners that help us propose new solutions in robotics. So our aim is to make complex structures affordable, and I will leave the floor to Jean-François to explain that.
Well, just to explain the title that I found perhaps representative of what we do in the laboratory. The first thing is, what is a complex structure? Because actually I don't think it exists really a simple structure, a simple architectural constructions. It's always complicated because you have a lot of parts to put together, to process. And it's also prototypes. So, but we can agree that the complex structures is when you are in non-standard conditions, non-standard geometries, non-standard dimensions, non-standard materials, eventually, and perhaps also innovative materials, and you have an unusual number of different parts and interfaces. The second thing is, why do we need complex structures? Very often it's to better evoke an architectural, an artistic message. We saw a beautiful thing in the first presentation, to fulfill non-standard requirements, but it can be also to optimize just a structure and process, and so to preserve consequently resources from energy and materials aspect to be more eco-friendly. And our laboratory is more devoted to the two last points. We are not relevant for the two first. And you understood now that I'm about mechanics of materials. So one of the paths we follow to make structure more affordable is to think mechanics of materials. It's very important. It's a little bit obvious, of course, but just very quickly, few examples. For the first metallic bridge in England, it's a very beautiful bridge, but you can see that it works just like a stone arch, and everything is in a compression, and we have to wait several years and many great researchers to propose some beautiful structures where the material is really at its best in tension and in compression, both tension and and compression. It's the same for concrete. The first bridge of Louis Vica, another alumni of old alumni of École des Ponts. It's a beautiful small bridge. You can see the scale with a pigeon, with a bird, but it's very close to also to an arch, to a stone arch, and here also we have to wait many years to have this kind of bridge, thanks to Freycinet using the pre-stress technology. And now with new materials as ultra high performance concrete, we go further, and we also can propose innovative typologies, very thin parts. But these thin parts become a new problem because you can have some high order problem like buckling, for instance. And so we proposed recently an alternative, and we propose to revisit the past, because if we think about ultra high performance concrete, finally it's a champion of compression. So we can reinvent the arch with this kind of material, and to avoid the buckling problem, we can also revisit the truss concept. And now with digital construction, this kind of bridge may be possible. From a simulation point of view, it works. We just have now to build it. And it's the same for, you can now mix a lot of different materials. We saw such an application also in the previous presentation. We can mix concrete, ultra-high performance concrete, and wood and glulam. You can think about composite materials with wood honeycomb, for example. And, on the right, just this example is we glue concrete on timber beams, and we insert also carbon fiber strips between the lamina of wood, and it provides a mean to stop the crack and to obtain a multi-cracking pattern for the timber beam, and you can also, by this way you can improve the performance of the beam, and you can delay the final rupture of the beam. Another example is to play with we also spoke about anisotropy in the previous presentation, and with some materials that you can find now, for instance, Techniwood from Techniwood company, you can play more and more with anisotropy, and you can, wood is anisotrope, but you can also use this kind of material. And we made a prototype for Bouygues, and it's patented now, to propose a building floor involving concrete and this kind of material, and it's very efficient. We have a specific test for composite materials, CFRP, GFRP, fiber reinforced plastics. They are now really they are used a lot in a lot of construction, in bridge, in buildings. Here you can see a lot of application all around the world. What are their strengths is, of course, you know that, I think, lightness, design, formal richness, fabrication, function integration. We have a small presentation for one of our PhD tomorrow afternoon about function integration. Thermal behavior is something very important now with new rules. And but perhaps the more important, the thing we like in the team is to play with strength and flexibility of this kind of materials. It's something very new for construction materials if you expected perhaps natural materials. And what are our weaknesses? I think the most important is that it's still in an incremental innovation scheme. It means that a lot of composite structures just copy a steel structure or wood structure, and it's not I think, the only way to follow. And flexibility for stiffness, it's something really amazing. You don't have other materials with this kind of behavior. And it's not something, and we want to play with flexibility for stiffness. You can see that it exists some previous attempts, and here you have in Iraq traditional housing using reeds, a bundle of reeds to shape a structure and to obtain stiffness, finally, to obtain a real structure. So it's why we try to follow. We have made several attempts. One using an old concept of Da Vinci. We have just fabricated a deck, a curved deck, and we remain it flat with steel cables. And these cables became, because they are tensed by the elastic bending of the deck, these cables became columns, and it's a very light way to put a column on a footbridge. So we have also proposed more futuristic attempts, more difficult to sail, I'm afraid of. It's a real pre-stressed bowstring. The arch, finally, is straight pipes, straight CFRP pipes that we have bent, and the bending is remained by all the cables and the deck, the platform. And it's very efficient from a structural point of view because it's a all pre-stressed structure. But the main of our works in this to obtain flexibility, to obtain stiffness with flexibility, is about our research about elastic grid shell. I think you all know here what is a grid shell. It's just a very smart way to obtain complex shapes with a very simple flat grid. It was proposed by Fry Otto during the 70s, but more especially with wood, and we propose to adapt this technology to composite materials, because composite materials are really better than wood for this purpose. You can see some pictures. And we have finally made about 10 years of research about composite materials, about materials aspect, technological aspect, structural aspect, shape aspect. We have really investigate a lot of research aspect of grid shell. We also made a lot of scale 1 prototypes, and to do that, of course, we needed help, and we have always find help in test engineering and theory construction, and I take the benefit of this presentation to help them again. And here you can see some pictures of our scale 1 prototypes. The most achieved, and this we prefer, of course, is Créteil Temporary Cathedral. It's a beautiful structure. But we continue to try to find mechanics of material interest, and more recently we proposed to replace the roofing, the canvas roofing of our grid shells with ultra high performance concrete, because it's very interesting. You brace the structure and you obtain something more fleshy, of course. And we also start some works combining grid shells and vegetalization for urban aspect to, for instance, fight against heat island problem. So I hope I succeed to interest you with mechanics of materials, and Romain will speak about his passion, I think, complex geometries and mathematics.
Okay, so thank you again. So we realized about 4 years ago that there was a need to kind of meet technology and complex geometries, and we needed better tool to assess the constructibility of the objects we were building. And for that you need geometry and mathematics. But before I get a bit more into detail about geometry, I just want to go back to the notion of complexity in architecture. And actually a good way to measure the complexity of an object is just to count how many pieces you have to assemble to get the object. So if you want to build the 2CV, an iconic French car, you need approximately 10,000 pieces. If you want to build the Concorde, you need to assemble approximately 100,000 pieces. But if you want to build the Eiffel Tower, you will need 2.5 million rivets. So the building industry, it's not the only aspect that defines the specificity that's not the only aspect that is specific to the building industry, but you have to assemble in the end many parts together. So how did we manage this complexity? If you look at the history of architecture in the 1950s, it was all about mass standardization and mass production with modernist architecture. So you see an example that is in Paris, but there are many examples all over the world. And you see here a more recent example from the years 2010, designed by Knipper-Sedgwick, where that is a good example of mass customization. You have a complex geometry, and every beam, every panel, every connection detail is different. So this is made possible, of course, because you have digital means to fabricate these objects, but also because the designers have good tools to manage the geometry and its complexity. So our first encounter with this problems of geometry was actually with the construction of some elastic grid shell. So just to recall a bit the construction process, this is the temporary cathedral in Créteil. So this is a flat grid assembled on the ground. It's a square grid, so you have an equal edge length. And because of that, it has no shear stiffness, so it can just deform like a piece of cloth that you will drape on any shape. So when you lift it, it just gets its double curvature. The problem we faced, that was faced in the lab, was that some shapes cannot actually be covered with a constant edge length. So you cannot apply this construction principle. The reason for that is that some angles becomes very sharp, and you cannot just cover the shape. So we tried our best with optimization algorithm, but for some shapes it was impossible to find a solution. So when you have a problem like that, you get to see a mathematician, and you will ask him, "Does my problem has a solution?" And generally, it will answer maybe, or it depends. So we went to see some mathematicians, the CERMIX research group, which is a lab in computational mathematics. And we asked them, can we cover any shape with a constant edge length? Because we will like that very much to be true to do elastic grid shell on very complex geometry. And they told us, well, it depends. So it depends if you allow yourself to introduce singularities. So singularities here, it's just the place where you have the red lines meeting, and you have more than 4 lines meeting at the same point. And provided you allow yourself to introduce this kind of change of rule in the way you design your pattern, then you can mesh much more complex shape than what we imagined. So that's one way you can manage complexity of geometry. It's to work with mathematicians. We have yet to build a grid shell with this method, but we are pretty confident that we'll achieve to do that. But you have another way. It's just to look back at what has been done in the past. And the reason for that is that architecture and structural engineering are cultural discipline. We're really rooted in and we make constant references to what has been done in the past. And indeed, you have some marvelous achievements of people who didn't have any computer or any sophisticated mathematics, and it's interesting to just ask how they managed to do that. And to me, what is very striking is that the tools that we're using for shape representation for architectures, if you're using Rhino, for example, these tools were developed for the automotive industry. And I hope that I convinced you that the automotive industry is very different from the building industry, because you have much more pieces to assemble in a building. So this is the Citroën DS. It was released in 1955, and 2 years after the first algorithm that will eventually be generalized to NURBS modeling was invented by Paul de Casteggio. So that's really kind of the car that triggered all these reflections on shape representation in the automotive industry. But the thing they wanted to model was, for example, the door or these parts that are roughly the size of the car. So it's very different from the problems we have in the building industry. On the other end, if we look, for example, at the Arles City Hall, it was completed in 1676, so quite a long time ago. And you can be sure that they had no knowledge whatsoever in geometry or differential geometry or computing, and there is a good reason for that. So it was completed 100 years before the birth of Carl Friedrich Gauss, who invented differential geometry, and it was completed 250 years before the birth of Alan Turing, so who is one of the fathers of modern computing. So it's interesting just to ask why, how they could manage this complexity. And they managed this complexity because they had tailor-made tools for shape representation. And you mentioned in your talk descriptive geometry. It's really the idea of representing an object with different projection, a plane view, an elevation. That's something that is very efficient because if you know two projection of a point, if you know two projection of a point, then you will be able to reconstruct its coordinates in 3 dimensions. The process can become a bit tedious if you have a very complex geometry to represent, and that's part of the reasons why this eventually was replaced by CAD modeling. But all the vocabulary of descriptive geometry is still used by architects, even if we don't make this reference. So part of our work was to reinterpret this vocabulary, these tools for representation, but to turn it from a tool for shape description into a tool for shape generation, a form-finding tool. And here you see that we kept almost the same plane view and elevation as this thing that is an elliptical vault that was actually proposed to cover the French Assembly in 1792. And we take the same geometry, same elevation, and we're able to construct from this information one unique shape that is covered with planar facets. And in that sense, we kind of merge the work of master builders on stereotomy to more contemporary structures, like this glazed grid shell, because you want to cover you want the glazing to be planar in order to be economical. So we use descriptive geometry to create design space satisfying construction constraints, and we explore these design spaces with structural optimization. So you can just have one objective, and you want, for example, to minimize the mass of your structure under certain loads, and you want it to be stiff and to have a certain buckling capacity. So that works, and you can also choose to do multi-objectives optimization, and for example, you want to minimize the glazed area and minimize the mass altogether, and it's not possible, and you have to find kind of a trade-off between these two objectives. So these are the few examples of structurally optimal structures that we found and that are covered with planar facets. And although the shapes are different, the underlying mesh topologies is the same. And that's kind of a limitation, because if you don't pick the right topology in the first place, then you might have trouble having a good resulting shape in the end. And that's really, we think, a limitation of some software we're using, where we're thinking parametrically, where we could think of in terms of topology. So that's an ongoing research together with the Block research group from ETH Zurich, where we try to propose not only form finding, but also topology finding with some prescribed boundary conditions. So it's the PhD of Robin Oval, which started last year. And you see some first example of this. And just to conclude on the merging between geometry, fabrication, and mechanics, there is a pavilion that is, you can see here at BMS in Versailles, that was designed by Nicolas Leduc. So again, a partnership with TESS and Viry Group, Viry Construction. It's a doubly curved shape that is approximated by developable strips. And these strips are bent into shape, so it really merges geometry, because you have this fitting of developable strips problem. You have mechanics, because you have to know how to bend your metal plates. And there is also robotic fabrication, or automated fabrication. So for that last aspect, I think Jean-François will conclude.
Yes, it's the last thing we want to address this morning, how digital and process and robots may help to make complex structure more affordable. It's the thing we start to looking for. Of course, there's a lot of means to use robots for construction. The first way, of course, is to they may help us to make the same thing we already do, but better and faster. Of course, there's a lot of business to do that. But for we researchers, we need to find something else and to find a very tailor-made application for robots. And perhaps the more trendy now is 3D printing. So we have started several works about 3D printing. We just have the robots, so we just start actually, but we developed some collaboration with Lafarge-Holcim and X3. X3, it's well known, I think you know them, as a startup who already made very beautiful things with 3D printing. So we start works with concrete and also with geopolymers. And Romain Duballet, PhD, another PhD, will speak about that this at the end of the morning, I think. Yes, so I don't want to spoil his presentation. The second thing we work on about robots is that the fact is that we need smarter and more adaptive robots. Actually, when you see a workplace or on-site fabrication, it seems difficult for a robot to be there with a very weak human, very unpredictable humans. It will be difficult for them to react to unexpected situations. So it's a very important thing to give our robots more intelligence, if we can say intelligence. For complex stereotomies we showed before, it's the same thing. If we made something very difficult, we want that robots may really help us to build the structure. And our robot may recognize the good block. How can he help us to pick and place the good block at the right place? It's something very complex, very difficult. And for these two purposes, the thing to do, of course, you know that, it's to need artificial intelligence. And it's why we try to use with Gaspard Monge laboratory. They are specialists of computer graphics and image analysis. It's a laboratory from École des Ponts, Paris Tech. And they are specialists of neural networks and deep learning. So we try to help their knowledge for our robots. And just to describe very quickly our works, what is the recipe if you want to use this kind of knowledge for robots? First, you have to train your robots. So first, you have to create an avatar, because it's more easier to work on your computer than with the real robot. So you have to create this avatar and feed him with a lot. And when I say a lot, it's hundreds of thousands synthetic images, also real images. You have to feed him with these images where he can see himself on the picture and the block close to him. And you just have to ask him where is the block. And of course, at the beginning, when he's young, he fails every time. So it's the principle of neural networks that he learns progressively. And you can see here, you have to also to put him in very different situations to be effective. And so progressively, he became stronger, and you obtain finally this kind of matrix, confusion matrix, where you have a beautiful diagonal. It means that what he predicted, it's what the real target. So at this step, you have just to plug your neural networks in the real robots and to make him to try if it works. So here you can't see on this in this movie, but there is two cameras which take pictures of the scene, and the robots may analyze these pictures with his new brain, and decide where definitely the block is. To be honest, on this picture we have helped him a little bit because we have not finished all our work, but it's also important for him and for his self-confidence to help him, I think. And it's important also for our self-confidence because it's finally something very difficult to just learn him with external pictures. So we arrived to the conclusion of a presentation. We spoke a lot about materials, mathematics, and robots. And the better way to conclude finally perhaps is to see a small movie, that project we have with students and with the platform building that Romain will present.
Okay, so very briefly, that's an ongoing project that we're fabricating right now. It's a structural innovation in the sense that we revisited the concept of reciprocal structures or inexorades. We propose new form-finding tools, and we propose also to do a bracing of these structures with planar panels that really give them more stiffness than usual inexorades. And it's a project that is supported by many industrial partners. They don't give us money. They give us really their expertise on the topic. You know, they add robotics. I think you know them. They work on software for robotic control. Simonin, it's a timber company. ABB for the robotic, and Wirt for timber connection details, and Schunk for specific tools that you will see in the video. So it was just the occasion to thank all these partners who made this project possible. So the reciprocal structure, just a few words about it. It's just a structure that's you find in vernacular architecture on all continents, in Asia, in America, in Europe, in Africa. And that's really something that you can revisit with digital tools for form finding and for fabrication. And we just milled the first beam for the pavilion last week. So you just see the milling of one beam with the new robotic platform. So the video is a bit slow. The robot is faster in real life. So there is like a feeder that will feed the robots with timber beams.
10 meter long
track. Yeah. And so then you just cut the beam at the right angle, and then the other robots will just mill all the specific connection details. So it's a bit slow, it's too bad. Anyway. So we are doing cuts to receive the panels. We are doing cuts for the connection details. And you see here the finished beam, we have 164 to go, so still a lot of work. And we wanted to conclude by thanking you and thanking all the members of the research group that have been helping us through the years. And you can find out more on our website, thinkshell.fr. Thank you.